Let's talk about subspaces of Rn. Just a few things that we really need to mention about subspaces of Rn. So a subspace of Rn is just the span of a set of vectors. A subspace of Rn is the span of a set of vectors. And that set of vectors is called a spanning set. A subspace is just the span of a set of vectors, and it's called a spanning set. The sub refers to being a subset of a vector space. So a subspace is a subset of a vector space that is itself a vector space. But that's not as helpful as how we want to think about subspaces. So we build a subspace by looking at the span of a set of vectors. That's called the spanning set. If the vectors in the spanning set are linearly independent, if the spanning set is linearly independent, then we have a basis for the subspace. A linearly independent spanning set is a basis for the subspace. A linearly independent spanning set is a basis for the subspace. The dimension of a subspace is the number of vectors in a basis. The dimension of a subspace is the number of vectors in a basis for the subspace. Some of you were using the word dimension, and now this is what it means. The dimension of a subspace is the number of vectors in a basis for the subspace. When we have a spanning set of vectors, we can always reduce it to a basis if we need to. So a linearly independent spanning set is a basis for a subspace. If we have a spanning set that is not linearly independent, we could just get rid of the vectors, some vectors, to reduce it to a basis. We can always reduce a spanning set to a basis. So if we have 3 vectors in a spanning set, but the third vector is a combination of the first 2, get rid of that vector, and those first 2 vectors will form a basis for the subspace. Any questions? So let's look at an example. Let's let H be the span of a set of vectors. I'm going to use H and H is going to be the span of a set of vectors, V1, V2, and V3. V1 will be the vector 2, 0, -1. V2 will be the vector 1, 3, and 5. And V3 will be the vector 3, 3, -4. So the set V1, V2, V3 is a spanning set of H. By definition, I just said H is the span of the set of vectors. That's the set of all linear combinations of the vectors V1, V2, and V3. Remember, span is the set of all linear combinations of V1, V2, and V3. But we notice that the vectors V1, V2, V3, that set of vectors is not linearly independent because V3 is just a sum of the first two. 2 and 1 is 3, 0 and 3 is 3, negative 1 and 5 is negative 4. So we note, this set of vectors, notice I didn't say the span of the set of vectors. This set of vectors, these three vectors, is linearly dependent. We can see that since V3 is just V1 plus V2. We couldn't use the multiple thing because there are more than two vectors. But I built V3 out of V1 and V2. If we did not see that right away, we could use a matrix to check. We can also check. We can also consider the matrix V1, V2, V3. The matrix V1, V2, V3. Notice I didn't call it the matrix H because H is not a matrix. H is the vector space. It's the span of those vectors. It's an infinite number of vectors. So we can also consider the matrix V1, V2, V3. So the matrix V1, V2, V3, if I find the reduced row echelon form, I know the first two vectors are going to be independent, but the last one is just a sum of the first two. So I do not have a pivot in every column. This set of vectors is linearly dependent. If I get rid of the third vector, I will have an independent set. V1, V2 is linearly independent. Same thing, if I drop this column, I'll drop this column and I'll have a pivot in every column of the matrix made up of V1 and V2. So since there are two, so V1, V2 is linearly independent, it spans the same as the three vectors, so it's also a spanning set of H. So also still a spanning set for H. So V1, V2 is a basis for H. V1, V2 is a basis for H. So we can say that the dimension of H is 2. The dimension of H is 2 because there are two vectors in a basis. Now, this does not mean that H is equal to R2. It can't be. The things in H have 3 entries. The things in R2 have 2 entries. So H is a 2-dimensional subspace of R3. H is a 2-dimensional subspace of R3. R2 is not a subspace of R3. They don't have the same number of things. Things in R3 have 3 entries. Things in R2 have 2 entries. One cannot be the same as the other. H is isomorphic to R2. That is, it looks just like R2, but it is not equal to R2. That is an important distinction that some of us weren't making during the test. H is said to be isomorphic to R2, but H is not equal to R2. Isomorphic is a different kind of equivalence relation. Just like a matrix is not equal to its reduced row echelon form, it's row equivalent to its reduced row echelon form. Any questions? All right. One of the things that we're going to want to do with a basis is, since V1, V2 is a basis for H, it's a linearly independent spanning set. That means every vector in H is a unique linear combination of the vectors V1 and V2. So that's what we get from basis. Basis. Every vector in H is a unique linear combination of V1. I'm having trouble with my squirrely brackets. Oh, actually, I don't even need them. I'm just going to say and. Every vector in H is a unique linear combination of vectors V1 and V2. We get every vector because we have a spanning set. So isomorphic just means there's a one-to-one invertible. There's an injective-surjective transformation from one to the other. So we can map everything in H to a unique vector in R2, and we can go back again. We get every vector in H because V1 and V2 is a spanning set. So every vector, because V1, V2 is a spanning set. That's what it means to be a spanning set. Everything is a linear combination of those two vectors. We get unique because the vectors are linearly independent. Unique because this set of vectors, V1, V2, is linearly independent. This means, so since every vector in H is a unique linear combination of V1 and V2, that means every vector in H has coordinates relative to the basis. Every vector in H has coordinates relative to the basis. So every vector in H, I have to switch to a new page. So many notes today. So that means every vector in H is a unique linear combination of the vectors V1 and V2. If we name the basis B, it's often very helpful to have names for our bases. So if we name the basis B equals V1, V2, then we can write, every vector in H is a linear combination of B, the vectors in B, the basis. Then we can write the coordinates of every vector in H relative to B. Let's not say, let's write. We can write the coordinates of a vector in H relative to basis B. We can write everything in H as a unique linear combination of the vectors in the basis B. So that means every vector in H has coordinates relative to the basis B. Coordinates relative to B. I know you're all thinking, do we have notation for this thing? And of course we have notation for this thing. So vector v3, if you recall, was 3, 3, negative 4, and it was 1 times v1 plus another 1 times v2. So we would say that the coordinates of v3 relative to the basis b, I use a script b, pardon me, relative to the basis b are 1, 1. Notice that the coordinates are in R2 because the coordinates are in R2 because H is a two-dimensional subspace of R3. V is in R3, but the coordinates of V relative to B are in R2 because H is a two-dimensional subspace of R3. The coordinates are in R2 since the dimension of H is 2. But the vector V is in R3. That is a V3 with a subscript of a script B. You put it in square brackets, and you subscript the name of the basis. And that's the coordinates of V3 relative to B. And it tells you the unique linear combination of the vectors V1 and V2. If this seems like a lot to take in like 10 minutes, that's only because it's a lot to take in 10 minutes. But you've already been doing this. So think of the point 5, negative 3 in R2 is a linear combination of the standard basis vectors. So the standard basis for R2 is 1, 0 and 0, 1. And this vector 5, negative 3, those coordinates say take 5 of the first vector minus 3 times the second vector. It's a linear combination of those vectors. Whoops, there we go. We want to be able to write everything in a subspace in terms of as a linear combination of the basis vectors. And when we do that, the unique linear combination that we get is called the coordinates. They're called the coordinates of the vector relative to the basis. How's everybody? If this seems like a lot, that's only because it's a lot. I just did about 5 sections in chapter 4 in 10 minutes. Because it's all related to things that we already know. We're just putting different names on things. So we had to have our name game and our word game really in place before we start moving on to add more to it. Any questions? Comments? Snide remarks? How's everybody, okay? All right. There are, last thing, when we're given a matrix, there are 2 important subspaces of Rn to consider. So let A be an M by N matrix. There are 2 important subspaces defined by the matrix A. 2 important subspaces defined by A. The column space of A. Oops. Denoted column space of A is the span of the columns of A. and the null space of A. Denoted null space of A is the solution set to AX equals 0. So there are two important subspaces defined by a matrix. The column space, which is just the span of the columns of A, and the null space, which is just the solution set to AX equals 0. We have to combine this information with everything that we know about a matrix and its columns. So the null space of A will just be the 0 vector if the columns of A are linearly independent, because AX equals 0 will only have the trivial solution. When we're talking about subspaces, we want to think about the span of a set of vectors. We want to find a basis for that subspace. That should be our goal when we're looking at when we're thinking about subspaces, because we want to think about what the building blocks of that space are. So the column space of A is the span of the columns of A. So to build a basis for the column space, we start with the spanning set, which is just going to be the columns of A. But we want to cut that down to a basis. So we find where the pivots are in the columns, the pivots are in the matrix A. We take the pivot columns from A, the original A, not the RREF. Take the pivot columns of A, that will be linearly independent, and it will span the same set. That will be a basis for the column space of A. For the null space of A, if we just write the solution set to AX equals 0, the vectors that are attached to the free variables in the solution set, those will form a basis for the null space of A. That'll tell us the dimension of the column space and the dimension of the null space. And once we have a basis, we just need to practice writing one vector as a linear combination of those other vectors, and we've got coordinates. And all of chapter 4 is falling into place, even though we're still in the midst of chapter 2. Any questions? All right, let's pause the video here because we're well over time and talk about where we're going to head next.